I'll be talking about quantum technologies in gravitational wave detectors, although this will not be a survey of all possible quantum technologies, but just a view of what kinds of things are useful to know about in the context of the history of gravitational wave detection using interferometers and the near-term future. So it's some lessons on where we've got to so far and what that means for the next generation. So quantum noise, I think it takes up a lot of our space, and we like to think about quantum noise and gravitational wave detectors because it occupies so much of the sensitivity band. Or what I mean by that is we show these plots, these kinds of strain spectral densities, where we take all of the noises that we can imagine that might affect our sensitivity, and we translate them into strain. And then we put them all in the same plot so that we can see which ones are going to limit the astrophysics that we would like to do. And the way things have gone in the history of development of interferometers, quantum noise winds up limiting the detectors over most of the band where we expect to see signals. And that quantum noise has this frequency dependence. It goes up at low frequencies and goes up again at high frequencies. That is a mix of the actual characteristics of the noise itself, but it's combined with the response of the detectors to signals. So the noise injected itself is effectively flat. It's white in power, so it's a flat spectrum, but the response of the detector declines at higher frequencies, and that's why the quantum noise goes up at high frequencies. And over the past few decades, we've spent a lot of effort in understanding the quantum noise, how to shape it within the detector, and how to manipulate it before the quantum noise arrives in the detector in order to take advantage of the shapes of the other noise curves. So one of the aspects of quantum noise that is different from some of the other ones is that it's a little bit easier to manipulate the particular shape of it with relatively small changes to the parameters of your detector in order to maximize the sensitivity. If you take it that thermal noise is a very hard problem to solve, or seismic noise or local gravity gradient noise are hard problems to solve, then you can try to change the design of your detector so that the quantum noise is hugging those other noise curves in order to do a sort of economy of noise in order to get the greatest sensitivity you can. So when we talk about quantum noise in detectors, I just want to point out that gravitational wave detection is a linear quantum measurement process. And this is a formulation from Braginski from 30 years ago or so, where he formulated this way of thinking that you have a signal that you want to measure, in this case, G, which is our gravitational wave, and a probe and a detector. And not everything is quantum. So the gravitational waves, of course, are not quantum, and the test masses are also not quantum. The test mass is our probe for the gravitational wave field, and the detector, in this case, is the laser light. So everything we do in order to have the laser light probe the position of the test mass, whatever physics influences that is the physics of our detector. And the light itself is quantum. And that is the origin of the quantum technology that is required for gravitational wave detection. So the quantum bit is only the optical field. And that's why when we talk about quantum noise and quantum technologies and quantum squeezing, as Jan highlighted earlier, we're always talking about the laser. We don't need to worry about any quantum mechanics of the test mass. And although we would like to see quantum mechanics of gravity, that's not part of our remit here. In interferometers in particular, so in a Michelson interferometer, like one that is constructed to detect gravitational waves, a key realization from many years ago was the source of quantum noise in an interferometer. And this gets at something that Jan was describing in an answer to one of the questions, which is that the gravitational wave appears in the differential mode of the interferometer. So in this very old diagram, we have the input field coming from the laser, and in this case, it's a delay line. So rather than having a cavity where the return field comes back to the beam splitter, the delay line comes in and the light bounces around, senses the gravitational wave, and then they come back and they recombine at a different point. And at this point, you could sense there would be an interference pattern between the two photodetectors. If a gravitational wave was to differentially move the two arms, there would be a difference in time delay. But if you trace the light back, you can see that light entering from this port, where there is no laser, would wind up at the same place, traversing a sort of time reverse trajectory of the light that you're injecting with the laser. And so drawing it this way helps us understand that although common mode rejection suppresses noise from the laser source, any light entering this open port here will also arrive at the photodetectors. And so this, what we call the open port, or any source of light coming from these open ports that will wind up in the same mode as the light that carries the signal and that hits our photodetectors, will show up as noise. And because the electromagnetic field is quantized and we're using optics to sense the detectors, there is a lowest quantum state, the quantum ground state, which we call the vacuum state. And that vacuum state mixes with the field at the photodetector, and that drives our quantum noise. And this is true for any open port in the interferometer. But the most important one is this dark port. And in the case of a detector where the beams all line up in the way we normally draw a Michelson, that open port is the photodetector itself. The photodetector doesn't produce any light. So if you imagine that it were a laser that were turned off, it's optimally coupled into the gravitational wave mode, or the mode of the detector that is sensitive to gravitational waves. So that is a source of vacuum coming from the photodetector. In the gravitational wave detectors, we often talk about, we classify the quantum noise in the two frequency regimes. At high frequency, it's shot noise, and in this kind of curve, it goes up because of the declining response of the detector. And at low frequency, we call it radiation pressure noise. The radiation pressure noise is just the same shot noise, but it's driving the motion of the test mass in exactly the way that Jan described earlier. And there's as you change the power input that you put into the laser, you can have more radiation pressure noise. So if you have a higher power laser, there's more shot noise fluctuations of the light hitting the test mass that drives more motion, and that creates more displacement noise at low frequency, masking the signal. But if you have low power, then you have less sensitivity or less driving of the test mass. So you have less radiation pressure noise, but you also have less photons to count at your photodetector. And so you have less sensitivity, where you're limited by the photon counting statistics when they arrive at the photodetector. So this is the combination of this radiation pressure noise at low frequency and the shot noise at high frequency is the total quantum noise. And as you change the input power in the interferometer, the minimum total quantum noise you can get where these two noise sources combine is called the standard quantum limit. So that's something that we often talk about. And there is an agreement within the community that anytime your noise goes below the standard quantum limit, we call that a quantum non-demolition measurement. But that's just terminology. I don't think there's anything special to it, but it's just so you know that when people talk about quantum non-demolition measurements in gravitational wave detectors, what they mean is they've gone below this standard quantum limit, which is just the locus of points of minima of the intersection of quantum radiation pressure noise and the shot noise. So the first quantum technology that I want to discuss is signal recycling. Signal recycling is where we add another mirror at the Michelson port at the output port of our Michelson interferometer. And this quantum noise is very different from what I described in this slide. So in a conventional interferometer with no signal recycling, there is the radiation pressure noise at low frequency and the shot noise at high frequency. In a signal recycled interferometer, you can get a much more complex system because you can have dynamical correlations in the light. So it's no longer so simple. And you can have these optical resonances, which can fall below the standard quantum limit. And you can also have optomechanical resonances, this very sharp peak here, where the entire detector is behaving like a bit like a mass on a spring, where the restoring force is provided by the radiation pressure of the light itself. So this was an important realization in the early 2000s or in the mid 2000s that there are these dynamical correlations of the light, and our old models of quantum noise in the detector were not sufficient. And so this is the first choice that we make in designing and manipulating the quantum noise spectrum of a detector is when you decide to employ signal recycling, you have to also make decisions about the specific parameters of the signal recycling, and those can have significant impacts on the quantum noise. So in this plot, I'm showing the total noise of advanced LIGO detector. This is a kind of plot that we were making in 2010 before advanced LIGO was, the design was frozen. And you can reshape the quantum noise to maximize the astrophysics in the presence of the other noise limits. So that's exactly what I was saying earlier, which is that we view the quantum noise as this flexible thing that we can adapt in order to take maximum advantage of the other engineered aspects of our interferometer. So all of these different noise curves here are just small changes to the signal recycling configuration. So the first one is this blue curve, which you just have if you don't have a signal recycling interferometer. And the other ones are small changes to the microscopic position of the signal recycling mirror. And by microscopic, I mean a sub-wavelength position of the signal recycling mirror, because that alters the phase of the light that is reflected off the mirror, the signal light that is reflected off the mirror and returned to the interferometer, creating these dynamical correlations. So you can get wildly different quantum noise limited spectra based on small microscopic detunings of the signal recycling mirror. This has the benefit that you can make choices to search for specific kinds of sources without swapping out major components. But it also has the drawback that small offsets in the position of your signal recycling mirror, for example, if you don't know exactly where it is to this sub-wavelength precision at DC, not at AC, that you can wind up with a misestimation of the response of your interferometer. And so this has significant impacts on calibration. And there has been a lot of work over the past few years in understanding the impact of this particular issue on the calibration of advanced LIGO detectors. Okay, so now I want to move on to, so that's the first quantum technology, which we need to come to grips with, is that the interferometer itself and the microscopic position of the signal recycling mirror has significant impacts on the quantum noise response of the interferometer. The second thing that we want to discuss is a currently employed technology, which is quantum squeezing. Quantum squeezing is manipulating the light that goes into that unused port of the interferometer. And here I show a plot from a paper that we call KLMTV. It's from about 2002, and it describes all of the possible ways that you can manipulate squeezing and then inject it into the interferometer, and then also possibly manipulate the signal light coming out of the interferometer. So that's input and output optics for the interferometer. So in this particular image, we have two filter cavities. So if we put the squeezed vacuum in and we bounce it off two filter cavities, then you can do particular kinds of optimizations. And having all of these different choices can lead to many different quantum noise limited curves. But effectively, what we have here is these ideas of injecting squeezing and manipulating the squeezing by bouncing it off of filter cavities as we do now are ideas from more than 20 years ago. And they're operating now, but it took 20 years of development to get them from the point of conception to operation and contributing to sensitivity in gravitational wave detectors. So let me take a step back now and just describe what we mean quickly by squeezing. So Jan covered this, what we mean by squeezing and how it goes. But the idea, what I'm showing here is the red arrows are phasors of the electromagnetic field. So they represent, if we were in each red arrow would be a phasor, and it'd be rotating around at the frequency of the electromagnetic field, but here we're in the co-rotating frame. And the different arrows here are snapshots at different times. The phasor is not perfectly stationary because of the quantum noise. And this is just describing what that pictorial representation is of how we go from a quantum noise, a quantumly fluctuating field, to what we call the ball on the stick diagram. So we have our phasor, which is fluctuating in time, and we just decompose that into a stationary phasor with some noise fields fluctuating in time. And then we draw the noise fields as a little fuzzy ball. Then we take that little fuzzy ball and we say a coherent state, so the output of a perfect laser. Perfect laser has some DC field amplitude, but it has some quantum noise, which is the fuzzy ball. A vacuum state, there is no coherent amplitude, there's no laser, but there's still a fuzzy ball. But we can manipulate that vacuum state, we can squeeze it, subject to an uncertainty relation, so that the uncertainty, the statistical uncertainty in the two quadratures, the amplitude and the phase quadrature, have to satisfy a Heisenberg uncertainty relation. And so if we squeeze it more in one direction, the noise increases in the other quadrature. And this is a fundamental thing. We cannot reduce the uncertainty relation. And so the squeezing means that although you're reducing one source of noise, you're always going to be increasing the other source of noise. In order to use the squeezing in a gravitational wave detector, we have to get it in. So we have to replace the vacuum field, which would ordinarily come from the photodetector, enter the dark port at the beam splitter, and then come back out and mix with the signal light causing noise. We need to replace that with some other field. And with the field we replace it with, we call a squeezed vacuum. But it could be any field. It doesn't have to be vacuum. It doesn't have to be squeezed. And the device we use to do that, as Jan described, is a Faraday isolator, which in reality uses polarization tricks. But we only need to worry about the fact that it has this three-port effect, where things coming in from one direction go out that port, and things coming in from the return port come back to the photodetector. So that's called a circulator. That in order to actually build the squeezing, or in order to actually inject squeezing into an interferometer, we also need to produce squeezing. And this is a shot of squeezing. So this is the first squeezing at this level and down low into the frequency band of gravitational wave detection. And I think Jan showed this exact same noise plot, but just at the lower frequencies. So this was in 2012. And this was the result of about 10 years of development from a coalition of gravitational wave experimenters who wanted to achieve what they called the requirements for using squeezing in a gravitational wave detection. And that was to develop 10 dB of squeezing at 10 hertz. And here it just got there. You see, it just got there in 2012 was when we first met that requirement to have it be useful for gravitational wave detection. Soon after was the first test on a full-scale gravitational wave detector. But before we get there, I want to talk a little bit about why squeezing and why using squeezing is technically challenging and the kinds of things that you need to worry about when deciding or designing squeezing and how to put it into an interferometer. And those are squeezing degradations. So I'm not talking about any of the particular technologies to produce squeeze vacuum or to manipulate the quantum field. There's many ways to do it. But ultimately, you will have some system, which is the squeezer on the left. It will produce some squeezing. So that's our squeeze light state, vacuum squeezing. But then it will go into your experiment. And As it goes into your experiment, it will encounter optical loss because none of our optical components are perfect. And I know Matt and Jan both touched on this. The optical loss, we model it as a beam splitter, where the squeezing comes in one port and vacuum light is coming in the other port. So this is quite a realistic model of loss. If light will be lost and just disappear to either scattering or absorption on any particular optical component, then that loss becomes a source of unsqueezed vacuum. And that unsqueezed vacuum is combined with your squeezed vacuum, and it creates extra noise. So it increases the noise a little bit in your squeezed quadrature. Then, as your squeezed vacuum propagates, it will bounce off of components in your experiment, and those components might be moving from any kind of noise source, and they will rotate the squeeze angle. So the squeeze angle is the actual phase of the optical field. So this angle of the squeezing here is relative to the phase of the optical field. So any microscopic motions, sub-wavelength motions of any components will rotate the squeeze angle. And when you rotate the squeeze angle, you take a little bit of that extra anti-squeeze noise and you put it into the quadrature that you're trying to squeeze. So you wind up, after a combination of loss and phase errors or phase noise, with something that looks much less squeezed than what you started with. And there are some theoretical plots here of the impact of these two effects. And what I want to point out from this is 5% loss is this highest curve. So that's the lowest loss curve plotted on the right here. That's not so bad. 5% total loss is pretty good. And what we see with 5% loss is no matter how much squeezing you produce with your squeezing system, whether it's a crystal or atoms or an optomechanical system, if you have 5% loss, your benefit tops out at less than 14 dB. It tops out at about 12.5 dB of squeezing. So even if you're making 50 dB of squeezing, if you have 5% loss, you only get up to 12. And if you have 15% loss, which is a more realistic number in a very complex optical experiment where you have hundreds and hundreds of components, each of which that have some finite loss, you top out at about 8 dB of measured squeezing. So in order to get 10 dB of observed squeezing, your total loss in the entire system has to be between 15 and has to be well below 15% and roughly about a 10 to 9%. On the left here, I also want to point out one of the traps for squeezing, and this is the phase noise. So here we're increasing our produced squeezing as we go to the right, and the different colors represent different amounts of phase noise. So if you have 100 milliradians of phase noise, which is not very much phase noise, that's 1/10 of a wavelength of RMS motion of all of your optics in your path, then by the time you get to 20 dB of squeezing, you have zero benefit. So all of the observed squeezing has gone away if you have 100 milliradians of phase noise. And the phase noise, of course, is has a bigger impact as you generate more and more squeezing because that's the rotation of the ellipse. And that's the anti-squeezed quadrature rotating into your squeezed quadrature and ruining your measurement. In LIGO and in experiments here at the ANU, we typically get 10 to 30 milliradians of phase noise, which is pretty good. It's hard to get much better than that. So this also places limits on how much squeezing you can realistically observe in a complex experiment. That said, it's all been done. So squeezing has been done in gravitational wave detectors as we are all aware. But it's been a long history with decades of development. And that's a point that I just want to echo from Jan, that the squeezing idea was first proposed in 1981 or so, and the first squeezing in the audio band at all was observed in the early 2000s. Squeezing reached 10 dB in 2012, and it was it's running in advanced LIGO in 2019. So this is a plot from 2019 showing squeezing routinely used in advanced LIGO. And there were some demonstrations on large-scale interferometers in the interim on GEO in 2011 and a LIGO interferometer in 2013. And of course, squeezing is also used in Virago now. So next I want to go to the next technology.
Robert,
and
would you be able to wrap up in the next couple of minutes?
Yes, absolutely. I'm almost done. Thank you. So Jan gave a nice introduction of why we need frequency-dependent squeezing, and I just want to highlight again the time that it took from this. So here I'm putting up some plots from the LIGO Scientific Collaboration Instrument Science White Paper from 2012. So in 2012, this was a concept that needed research to be done. And Matt, who I think has left, was a key figure in realizing this research, doing the first test at the audio band. But in 2012, this was research that still needed to be done. And 13 years later, it's running in advanced LIGO. So this is a simplified cartoon of the frequency-dependent squeezing in advanced LIGO, where the squeeze angle is different at the high frequency and the low frequency, where the rotation needs to happen at 100 hertz. So in order to make that rotation happen, you need something that stores light on the time scale of 100 hertz, and taking into account the possibilities of optical coatings and optical losses, it was worked out that a 300-meter filter cavity was about as short as you could go in order to store the light long enough without it just being dissipated by the finite optical losses in that cavity itself. And now it's functioning. So I think this is a great story of how quantum technology goes from conception to implementation. It is challenging, and I put up this simplified diagram to show just how many optics the squeezing gets bounced off of before it actually enters the interferometer. There are many, and none of them can be contributing to the optical losses or to the phase noise. One last thing that I want to mention in terms of degradations is it's not just the losses and the phase noise, but that the mode mismatch is another issue that I haven't covered at all, but is a piece that is quite complex. When the squeezing is bounced off of multiple cavities, mode mismatch has interesting effects on the squeeze quadrature. And in particular, it can do an extra rotation of anti-squeezing into the low noise quadrature, which so that is particularly challenging, and it is one of the things that is we are grappling with in advanced LIGO right now. So I just want to conclude by pointing out that squeezing, like many other aspects of gravitational wave detection, requires decades of R&D before implementation, but it's now contributing materially to the sensitivity and the event rate. And so the event rate that we see in the increase in event rate in O4 is in part due to the implementation of frequency-dependent squeezing. But the quantum technology is just an expression of exquisite classical engineering. The challenges in the quantum technologies are all in the classical bits, in getting the low noise optics and getting the high precision positions of all of the other components in the interferometer or in the detectors. And that's it. Thank you. And I want to thank you for having me and having me speak.
Thank you very much, Robert. It was a very comprehensive summary of the use of quantum technology in gravitational detectors. Other questions? Yes.
So you mentioned that in low frequency, there will be radiation pressure, which will cause the mirrors move. So I was wondering, does the mass of the mirrors play any role? Like if the mirrors are more massive, will this motion be less, or we are bound to keep the masses of the mirrors within some limit?
So having more, yes, the radiation pressure at low frequency is a force. And so the response of the mass in terms of displacement goes down as you increase the mass. And that is in large part one of the reasons why like A sharp is 100 kilograms and Cosmic Explorer is thinking of a 400 kilogram test masses. So that is the practical limit is how big of a test mass can you suspend, I think, is how much can you hang using the kinds of materials that we have that have a high enough quality that the thermal noise is still low. So it's a practical challenge.
Yeah, thank you for this talk. Very interesting. What future improvements in quantum measurement technology are planned for O5 and beyond?
So in O5, we are looking to increase the robustness, I think, is the key thing. So in O4, we are observing 6 dB of squeezing. So that's a 6 dB improvement in the quantum noise. But that's only at Livingston. At Hanford, it's more like 5 dB. So we want to get them both up to a bit higher squeezing. Another issue that is being worked on for O5 in particular is that the squeeze light sources appear to be generating less squeezing over time. So some components are just being replaced. So the LIGO squeezers are the first squeeze light sources that have been run for years without stopping. Most squeeze light sources, you run your experiment and you run it for a few minutes or a few hours, and you take your data and you publish your paper. As an appliance that needs to run, the LIGO squeezers are the first one, the gravitational wave squeezers are the first ones to run for years at a time. And they're experiencing some degradations, which we don't fully understand. So we're also replacing some components to bring them back up to the level that they were before. And the last, another thing that is being done for O5 is improving some of the mode matching. Not by, so that's the shape of the beam and the shape of the beam that is squeezed and making sure it's matched perfectly to the shape of the beam within the detector through some active components that can reshape the beam. So what we hope that gives us another lever to make sure that the mode of the squeeze light source is matched better to the mode of the detector.
Thank you, Robert. I have actually another question now. So we have been having some discussion in the earlier part of the meeting about the possibility of measuring post-merger oscillations of neutron stars, etc. So we know that there is the effort in Australia going on in building the high frequency detector. So can you quickly summarize what are the challenges in attaining these high frequencies, narrowband sensitivity?
Yeah, so I think the main challenge in achieving that sensitivity at high frequency, especially on a short baseline, ultimately the total sensitivity that you get is always going to be related to the stored energy in the detector. So in order to get high frequency sensitivity beyond what anybody else has, you still need more energy stored in the detector. And so that's more optical power circulating in the arm cavities. And that generates all of the challenges of high power, which we are still grappling with as a community, in terms of absorption, in terms of parametric instabilities, other optical power-based instabilities. That is very challenging. And it will take work to develop the solutions to those challenges.
Okay, thank you very much, Robert, for this very comprehensive and a nice summary.